So our third speaker will be Anne. Right, Anne is a PhD candidate at George Mason University. So his dissertation focused on improving user quality of experience in immersive experiences through the analysis of security and performance in video streaming systems. And today he's going to talk about how you can steal the keystroke so during the VR experience. And this is one of those awarded lab papers in NDSS. Yeah, takes the stage.
Thank you, Dr. Chen, for the introduction. So this paper is a collaboration between George Mason and Georgia State University. So virtual reality, we know that it's popular and it has many applications. And in those applications, user usually would store sensitive data. For example, in gaming, user may store credit card information to buy gaming services. In healthcare, patients may store their health record information. And in education and training, various user behavior data can be stored inside the app. And malicious actors may, of course, want to gain those sensitive data for personal gains. And we need to protect the sensitive data to secure the virtual environment and ensure the user quality of experience. And in existing work, typically they use authentication scheme to protect the sensitive data. The assumption here is that by prevent the unauthorized access to the hardware, the HMD system, then the sensitive information might be secure. We have some example like biometric by authentication or knowledge by authentication like PIN, code, and password. However, there are some attack types that can bypass the authentication system, and one of these attacks is a side channel attack, which aim is to capture side channel data that is available to public through the interaction between the user and the HMD system. Some example like when the user wear the HMD and enter the PIN code and passcode, the attacker may use the camera to capture visual information like head movement, hand movement to infer the keystroke identities. And also other attack can capture the wireless signal fluctuations. And this attack doesn't require access to the HMD and therefore the authentication. And in this paper, we consider another type of side channel is the acoustic signal emanate from the controller. The question here is that if the attacker places a smartphone to record the sound of the keystroke when the user entering the passcode, then it's possible for the attacker to analyze those sounds to recover the keystroke identities? In order to answer this question, we first investigate the principle when the user interacts with the virtual keyboard. And so in order to make a keystroke, user have to handhold the controller, and then they have to move the controller around in order to move the virtual cursor on a virtual keyboard. And when the virtual cursor reaches a target key, the victim will click on the controller to commit a keystroke. Now there will be a clicking sound. And the attacker, assuming they already have a smartphone nearby to record the sound, then we see that for each key in the virtual keyboard will occupy a unique spatial position on the virtual keyboard. So the direction of the arrival from the controller keystroke to the smartphone will also be unique. That means that if we can somehow analyze this unique sound to capture the direction of the arrival, we can associate with the key's identities. So threat model, we assume that user will enter the sensitive information in a confined setting like a shared environment in a library where the attacker can get close to the victim when the victim is enter the key code, and then he or she will place a malicious smartphone nearby. And the smartphone will record the acoustic emanation from the controller. We also assume that the attacker will know the layout of the virtual keyboard, and we don't have any further assumption, so there will be no malicious app here. There are three challenges associated with this problem. The first challenge is that the sound coming from the sound source coming from a 3D space, but the smartphone, it has an omnidirectional microphone, and we know omnidirectional microphone can only register the magnitude of the sound, but not the direction. Second challenge is that the relative position of the smartphone and the controller can vary between different attacks. Here we show two cases. That the smartphone can be placed in front of the victim, and in another case, maybe on the side. So how to handle this varying in the situation? The third challenge is mapping error, because the way that user achieve the destination could be sometimes different, maybe. For example, if the user move from the letter A to letter Z, he or she may shift the controller down, or he may rotate the controller. Both ways allow the user to reach the destination key, but the controller rotation are different. Maybe it's result in a slightly different arrival, which means that a little bit different in the key sound signature. So here we introduce Heimdall, a system architecture to launch the attack. It will have three modules corresponding to three challenges. First is the directional acoustic signal acquisition to register the sound in 3D space using the directional microphone. Second module will have an adaptive mapping between the direction of the arrival and the key to handle the varying between the phone placement in different attack cases. Third module will correct some mapping error from the previous component. And here is the first component. So we will utilize the existing smartphone, but we convert the omnidirectional microphone to the directional using a two-porous tube attached to the microphone on the top and the bottom of the smartphone. And this setup allows the omnidirectional microphone to register the direction of the sound. And then the signal will be the noise to remove the background noise. And then we will identify the clicking sound data. Basically what we did is we identify the signal peak, and then from the signal peak, we extract the temporal data segment surrounding the signal peak and consider that it as the keystroke clicking sound data. We also need to identify the keystroke section when the user interacts with an application. But fortunately, we see that the keystroke section, the pattern is more rapid but steady compared with other sections like launching the app or navigate the web page. So after we have the first model, the second model will deal with the varying between the different smartphone placement and the virtual keyboard. And here, first, we will need to have a baseline direction of arrival to key mapping table. What I did is that for every key in the virtual keyboard, we consider a standard smartphone position, and we will record all the angular position of all the keys on the virtual keyboard. And then during the attack, we will record the offset between the smartphone placement during the attack and the standard smartphone position. Using this offset, we can update the mapping table. And with this update mapping table, we can identify the key. From the signal data, we can extract and identify the angular position of the key. We match it with all the tables, entries in the table to identify the key identity. And lastly, the third model will fix some error on the second model, as I mentioned before, on the wrist rotation. And we want to utilize the temporal information between the consecutive key. For example, the latency between two consecutive key clicking, and maybe the controller moving direction. So how to use these two information? We model the problem as using the hidden Markov model. Basically, the observable variable is the latency between two consecutive keystrokes, and then the moving direction of the controller, and the keys will be the hidden state. And then after that, we use HMM to generate a sequence associated with each sequence is probabilities of that sequence. And then we can choose the sequence with high probability, but also the similarity with the original mapping sequence in the second step. So experiment setup, we select 30 participants. Each one will input 45 passwords with a length of 4 to 8. And we measure the accuracy for each keys, and we see the precision and recall across each key around 95 to 96%. We also investigate the impact of smartphone placement. Here we consider 5 rotation offsets and 3 base placement offset here in front of user, behind user, and on the side of user. And we see that in most cases, the performance seems kind of stable. And lastly, we also investigate the impact of environment. Here we consider different static noise like a desktop fan and air conditioner. We also consider some impact like the people talking and walking. And we consider 2 setup is in the lab and the library. Overall, we see that the performance is kind of stable. So in conclusion for this paper, we investigate and expose a security threat involved with the emanation of the acoustic signal from the controller. And then we propose an architecture called Heimdall, an attack framework that it can handle flexible smartphone placement among different attacks. And we evaluate this system regarding the inference accuracy and its robustness. Yes, so that's conclude the paper. Thank you.
Okay, we have time for questions. Yeah, David.
Yeah, just one quick question, and sorry if I missed it. Are you making the assumption that while the user is typing the keystrokes on the virtual keyboard, then the user is not moving? For example, if the user starts typing and then all of a sudden it turns 90 degrees, would that change your results?
Well, in current VR application, the virtual keyboard is fixed in most cases. So if the user makes a slightly movement like this, it does not change, unlike he steps outside in a very significant distance. Then the keyboard will be updated. But we say that is very rarely happen. In that case, very rare.
Okay. All right, thanks.
Hi, thank you for the great job. It seems that this attack is kind of affected by the individual people's kind of behaviors, right? Because people have different behaviors in terms of clicking. So I wonder, did you do like a user study, and like how many users did you study? And if you did you observe any kind of large variations between the behavior of different users?
I see. So we tested on 30 users, and actually user kind of already familiar with the keyboard layout in reality. So in the virtual environment, they don't have difficulty to find the next key. So there's not much variation between users. And furthermore, we all have the user to practice a little bit before actually going to the test. Yeah.
I see. So for the Markov chain model, did you have to, is that generalizable over different users? Is that the correct understanding? Or did you have to build a model for each individual user?
It's a one single model.
I see. Yeah. Cool. Thank you.
So nice talk. I have a question about 10 years ago, there's a work, 2011, using iPhone to record keyboard press. And I'd like to know what's the difference between your method and there. What's the advantage of using the angle instead of just the sound while key was pressed to do the keystroke identification?
I'm sorry, I did not hear you very well. Can you say that again?
Oh, okay. So in 2011, there's a work using iPhone 4 at a time to identify keystrokes. And so I wonder what's the difference or what's the advantage of using your method versus the work 10 years ago?
Yeah. I assume that the previous work, they work on a traditional keyboard. Is that right?
Oh, you're using virtual keyboard?
Yes.
Okay, I see.
So the virtual keyboard is not lying flat, and it's on the 3D space. And we know that omnidirectional microphone have the problem when identify object in 3D space. So it's different from previous works.
Okay, thanks.
So we have time for one more question.
Hi, nice talk. Zihao Su from UCSB. So it wasn't exactly clear to me. Like maybe I missed it. Like you used like single data to like locate the clicking, but like there's like the user hand pointing at the keyboard, right? So there's multiple spatial factors. Like how do you like position the user hand like cursor versus the keyboard?
Can you clarify the question again?
Yeah, so like I guess my mental model is that you have used the sound side channel to locate where like the user's position and rotation is, and then also where the keyboard is in front of them, right? So like how do you use just like one single sound like to like infer all that information? Just like some clarification.
I see your point. So my understanding your question is that how could you use the single sound and identify the position of the key, right?
Yeah, to like for like a high dimensional spatial data.
I see, yeah. So again, the virtual keyboard is always fixed. They doesn't change. User have to manually move the hand in the space such that the virtual cursor match the key. So the position of the virtual of the hand will be unique, right? When they reach a certain key, it has to be must reach a certain position in space. And therefore, the direction of the sound from the controller to the smartphone will be also unique. And since we use a directional microphone, we can capture that direction of arrival.
I see. So like assume to be calibrated instead of like say I open the app and then like place the keyboard at a random location.
Yes, that we already discussed is how we can identify the keystroke sections versus other sections. Because we already, from another study paper, we also point out that for the keystroke section, the frequency of the click is also faster and steady, versus when we exploring a web page, for example, the click will be less frequent.
Yeah, I don't mean the time, but like you can like open an app, like a random app on VR, right? And you can, like go to a random place in the room and then place a software, like a keyboard in front of you. So that would be like, an arbitrary, position, right?
I'm sorry, I did not get your questions.
So like you can.
So yeah, we
Okay.
are actually out of time. So maybe
we can talk.
Yeah, we can
after.
sure talk outside. Yeah, thank you.
Because I believe many people here are hungry. So let's thank the speaker again.